Okay, good afternoon, everyone. Let's welcome Ivan Novikov, presenting on bye-bye false positives using AI to improve detection. Welcome, Ivan.
Okay. Thank you. Hi. Hello, everybody. I'm here today to discuss and actually share our experience related to false positive things and how we applied machine learning neural networks to avoid false positives and how we actually solve this problem. I believe that it's pretty relevant problem for any attack detection things, not only for application security, but also for endpoint security, for APS, IDS stuff, or so on. So let me please introduce myself a little bit. My name is Ivan. I'm 13 years in InfoSec, 5 years here of Worm, and I do some sort of bug bounties, and I'm author of like 50 plus more researches. And my friend Michael and my really good colleague as well has 3 years in ML. He's not here, unfortunately, today, but he also involved in a lot of researches, at least 10 plus different researches and articles. And I designed a system, and Michael actually put it into the code. So what's the goal for this research? First of all, we decided to replace false positive incident response process, I mean production process, from that initial user action when user who was blocked by some sort of false positive mistake made by detection system or his or her capture action or email to support team with a request ID. We want to automate this process from this initial action to that time when our automation system will tune a rule in APS, ADS, or web application firewall, or whatever. Second point here is we want to be indifferent to that attack detection logic that made that initial decision. I mean, whatever it means, regular expression or some sort of tokenizer or sandbox detection system or another neural network, we want to design a system to be able to tune their rules and make decisions and actually correct some sort of other detection logic and be indifferent and what does it mean in terms of detection logic behind us. Point number 3, we want to apply this to real world, I mean to the wild world, and achieve results. It shouldn't be just a research about research. We need to adjust our own mechanism and tune our own detection logic and improve our own product. And it should be available open source as well. So as a result, I want to highlight that we don't want to invent yet another detection logic itself, like signatures NG or whatever, but we want to train neural network to improve existing algorithms. So scope and limitation. So for this particular task, for this particular research, we limited our data set by SQL injections payload. But it's not limited in a code somehow. It means in particular that you can replace our data source for SQL injection to data source of your, I don't know, XXX payloads, malicious payloads, and improve your own antiviruses or NG antiviruses. Or you can replace our data source by XSS and tune your WAFs related to XSS attacks or so. It's only limited by our data source. And point number 2, it's not for legitimate false positives. For example, vulnerable app could be designed specifically to interpret some sort of data as comments. For example, it could be phpMyAdmin or my web panel, like cPanel or whatever, or just other ways of control panels. We not designed the system to avoid this, but I'll address this problem as well a little bit later. And for example, if you want to protect, I don't know, your personal block, and you want to put a particular attack payload in a message field, and this payload will block, we'll never address this issue because technically this payload, we can count this payload as a legitimate false positive, right? We wouldn't address to the problem in this research. So I want to mention that my first time I started to work with neural networks almost 10 years ago in this pre-TensorFlow times, when we made everything from scratch. And I want to mention that never trust people who will mention that, okay, we will apply neural network to solve this problem. It's almost impossible to solve any single problem by machine learning if you never try to solve this problem by just ordinary algorithms. So I want to describe how we tried to solve the same problem before we even start to think about machine learning things. And we can mention 3 points here. Point number A. We need to define what's an attack payload itself in terms of formal logic. I mean, it should be a definition related to science. It should be differentiation in this like Turing machine terms. Only in this case, we will be faced with some sort of solvable problem. Otherwise, we can just be failed anyways. Point number B, how to detect attacks in theory with 100% accuracy. Otherwise, how it's possible to measure what we designed based on neural networks? Is it good or not? And it definitely should be solvable in theory somehow. And point number C, is it possible to implement this theory, or if not, why? If it's possible to just implement this theory to apply 100% accuracy, for what we need to design machine learning stuff? If we can solve it, not a problem. And nowadays, I want to describe each single point here. So, point number A, what's an attack payload? We've spent almost 1 year, even a year with an half, to just discuss and negotiate between each other to finally make this formal definition what this attack payload is. In emotional language, it seems like a piece of data, like a user input, that could affect some sort of parser or compiler like SQL, HTML, XXX, or whatever by injecting some commands. In more formal way, it's just an input data interpreted by some Turing machine that affect this Turing machine by some sort of instructions. Or another one variant, if some Turing machine can interpret some input data not only as data itself, but also as some set of instructions, this machine can be called vulnerable, and this data could be called as an attack payload. So, and this is a formal definition. Funny thing about the cybersecurity, like science, that it's not a science. I mean, it's impossible to buy a book and read some sort of things like, okay, this is a Turing machine, this is a formal model of this machine, and this is what the vulnerability is. We have no. We can study any university and they can cover only cryptography as a part of science, which is good, and all the rest, especially related to applied cybersecurity, it seems like hundreds of random facts. And that's how we define our payloads and how we put this one or like couple of hundreds random facts to some sort of formal way. Point number B, how it's possible to detect attacks with 100% accuracy in theory. Since we define it that we're working nowadays with Turing machines, parser machines, and definitely each single compiler, whatever it means, like SQL injection or HTML or whatever, could be defined by some Turing machine. Nowadays, we know that technically we just want to run these Turing machines and understand what the parser process is. Is it any instructions there or not related to this particular user input in theory? But there are 3 different problems we need to address to solve this. First of all, even for this narrow case of SQL injection, we faced with MySQL, MS SQL, SQLite, Postgres, Oracle, etc. A lot of different like ways of parsers, kind of parsers. Second one, we need to know all the initial parser states to run all the parsers, but parsers are recurrent. I'll address this problem a little bit later. And point number 3, just performance, which is definitely a solvable problem unless we will faced with a halt problem. So B1, so many parsers. It's addressable until we have no intersection in parser mechanics. I mean, in particular, lexical syntax, semantic analyzers inside these parsers. Otherwise, we need to split it into different machines and run them separately, which is also an addressable problem. And another one point here is, can we build one unified parser to cover all the syntaxes in one Turing machine? Yes, we can, but we will pay for accuracy in this case, because when we will combine every single SQL parser into one parser, we will miss something. So point number B2, I mean. We need to know all the initial parser state. So look at the first line. The first line describes a simple SQL injection vulnerability, and this initial parser state highlighted by a red color. We can just describe each single initial state related to select syntax, update syntax, insert, whatever we've seen before, and actually solve this problem. But we have an unlimited number of the states because they are behind recursively enumerable grammars like SQL injection. For example, these brackets. Who knows how many brackets were there on the left in this initial state? It technically means that we cannot enumerate it. But we can convert this original recursively enumerable parser to another one grammar like context sensitive or even context-free or even regular syntax to make it happen. And this Lisp style breaks, or as we call it, Lisp laws on us. But it's also solvable. And point number 3, it's performance. It's not only relevant to halt problem itself, because if there is a halt problem and we cannot actually pass this particular data through the Turing machine and to do not catch this infinite loop, since this machine relevant to some sort of real vulnerability inside an app, it's not our job actually. So if it was designed bad, it's not our job to fix this. Our job is to detect issues. To detect payloads. To address this, we can pay by memory. We can run as many instances, at least as many instances as different states we covered there, and then put data through them. And it seems like a cache warm up mechanism, also addressable problem. We can pay by accuracy as well, as I mentioned before, if we were able to design a kind of context-free or context-sensitive grammar or even regular grammar to cover everything and to actually to be relevant to our original syntax, but also to claim some new false positives. And funny is that if we were able to replace our initial and original SQL syntax, for example, by regular grammar, we actually will reinvent regular expressions. That's exactly what we will do in this case. We will do signatures, regular expressions. So, point number C, is it possible to implement this theory, or if not, why? So it's definitely possible to implement everything I mentioned before with all the limitations I mentioned before. And we've started with just SQLite parser, tuned to precede Oracle, Postgres, MySQL, and other specific lexems with some hacks, like how to remove these brackets to do not allow Lisp to laugh on us. But it's a lot of manual actions for single grammar. And to make it easy, we released lib detection framework to define grammars in a formal way and to allow to use this not only for detected action itself, but also for payload generation things. It's available at GitHub as well, and you can use it. No machine learning at all, pretty useful stuff. You can define your own grammar, whatever it means in BNF, put it there, define your own lexer, and generate your own payloads to train your machines or neural networks or so, or just use it to detect attacks. Pretty useful stuff. So finally, we decided to apply neural networks, the most interesting part of entire talk. We decided to use recurrent neural networks because we cannot limit length of our payloads, because it's just impossible to ask attackers to be short in payloads. That's why recurrent. We decided to apply an attention layer, an attention mechanism, because of our assumption that it's possible to make a decision about false positive by looking at some particular part of the payload, how we perceive these payloads by our minds, by our brains, right? We decided to do bidirectional recurrent neural network to cover semantic things when we can make a decision about what does it means only after looking back, after looking forward or controverse. For example, when you read in a line, you need to be able to come back to understand what was there, or you need to jump forward a couple of words to understand what does it means. That's why bidirectional. And we applied some sort of data preprocessing by additional heuristic algorithm, we called it tandems, to remove just equal sequences and our payloads to solve this Lisp smiles problem. So this is an architecture of the network we've built. It's an embedding layer plus a couple of layers or more of bidirectional RNN, in particular LSTM, but you can replace it to other other RNN cells, not a problem. Then max pooling things, and average pooling things, and attention layer, and everything to the output. It's actually it's not usual architecture, but we tried different things, and we decided to use this. And a little bit early, I described why. So it's available online by MIT license at our GitHub. We also released some sort of real data to test it during our ML hackathon. It's also available at Kaggle. And feel free to join this project. Feel free to apply your own ideas there. Feel free to correct us if we were wrong or whatever. And once again, it's limited only by this data set. If you have your own data set, you can apply different things there and achieve different results and tune your own detection systems. So how to use it? First of all, you need to prepare your data set or use our data set for SQL injection by running a simple command. This command will apply these tandem things to remove these Lisp smiles, and we'll create a vocabulary based on all the tokens, all the lexical constructions in your data set, and create this. And then you can train your network by this train pi. It requires TensorFlow 1.1 plus. And don't forget to give us a star at GitHub. So what to tune there? If you want to tune this system, if you want to, I don't know, make it a little bit better, if you want to apply different, and specifically if you want to apply different syntaxes there and train it to avoid false positive for your, I don't know, exercise detection system or whatever, you can tune number of hidden size of these hidden layers, right? Number of neurons there. We started with 256 neurons by default, and 2 layers. You can add more if you want to, but be careful, because all the time when you will add new neurons, you will spend more and more time to actually train the system, because it's pretty related to resources. You can change embedding size layer to make it smaller or bigger if you want to. You can play with attention hidden layer size as well. Usually it's 50% of RNN layer neurons. You also can change dropout if you want to. Interesting question here, and actually the last question I want to cover today is how to identify how many neurons I need to add there to actually achieve some sort of like valuable results. So we decided to apply some sort of like semi-magic logic. So we decided to take a look at amount of different lexems and tokens and initial syntax. We decided to try to convert this parser machine to some sort of like push down automat and understand how many graph edges we will make there in this case, and apply at least that much neurons to actually allow our neural network at least to train the same amount of edges in their graph. That's what we decided to do. And then we add a couple of more neurons. So I believe that it's a valuable logic, and as well as if we want to apply AutoML things and tune another one neural network to create a topology or find hyperparameters of this one, it's also possible. And we released in our blog an article how to apply AutoML to find hyperparameter of another neural networks. So what's next? The last point here is to cover legitimate false positives as well. As I mentioned before, if I want to protect my personal blog or if I want to protect stackoverflow.com, it's completely normal situation for these particular websites to achieve malicious payloads. And all the time when we will apply detection logic, this detection logic will produce a false positives for us. What we want to add there, we want to add some sort of metadata related to particular app we want to protect to reduce even legitimate false positives. In particular, it could be request parameters like a URL or parameter names or whatever, and we're still working on it because it requires to redesign architecture of this neural network at all, add additional attention layer related to specific parameter things. It requires for us to just define this DSL, how to name these parameters in the requests, and how it should be actually, how to build this vocabulary, all the other related things, and also requires from our side to pack everything together into one neural network topology and put it there, and we're still doing it. So feel free to join the project, feel free to share your minds, feel free to, I don't know, ask us to do something more crazy than we did. And you're very welcome here. Thank you. I believe that we have some time for question and answers.
There's a question that came online, so let me read it to you.
Cool.
Why not using a RASP that by definition would not have false positive on SQL injection? Instead of looking only at the user payload, it will compare the user payload and what is actually injected in the SQL query.
Yeah, sure. I expected questions about RASP, but once again, it doesn't matter how we will apply this detection logic or which types of false positive we will able to mitigate. RASP thing is the difference between like network-based IDS and RASP as where exactly we put the detection logic. And under the roof of any RASP, we will faced with the same signatures applied to the data in query parameters. You can avoid false positives between user data and this particular query, but then they need to, it still requires to apply some parser there to understand what happens there, to understand, like, is it related to the state analysis or not? And we were able to tune these false positives as well. So that's why.
Any other questions? No more questions. Thank you, Ivan, for your presentation. And on behalf of BSides, you get a gift.